My name is Paolo Favaro and I lead the computer vision group at the University of Bern. Thanks to the organizers for inviting me to this workshop. In this talk, I'll try to give some insights on unsupervised representation learning. We are all familiar with supervised learning. Given a dataset with images X and corresponding labels Y, one needs to train a model to map X to P of Y given X. The training uses labels Y that have been manually assigned to each data sample X. This is a well-established and effective technique that has been widely adopted in the industry. Here is an alternative to supervised learning. In unsupervised representation learning, one first trains a network without labels to map images X to features phi by defining a so-called pretext task that requires no labels. This step is called pre-training. Then, one trains a small network, possibly with one or very few linear layers, feeds the features learned during pre-training as input, and trains the small network on a small set of data samples with labels. This second step is called transfer. If one also allows the pre-training network to be updated during the transfer, then the whole procedure is called fine-tuning. Now you might ask, how do we define the pretext task in pre-training? In particular, how do we deal with the lack of labels? An approach that allows to do that is self-supervised learning. We will focus on methods that work on images, although self-supervised learning is applied also to other data, such as videos, audio, EEG, and combinations of signals, such as in the multimodal data case, where, for example, one combines images and audio. The next question that comes up is, why unsupervised learning? Here, I would like to give a few reasons why we should focus our efforts on unsupervised learning. I decided to work in unsupervised learning 8 years ago. The decision was pretty straightforward to me. I thought that supervised learning had a few problems. It is very expensive, requires a new large data collection for any new task, and in many cases data privacy is a concern. For example, in medical, insurance, and military data. So it is not always possible to distribute data to many workers to label it. Moreover, labeling can be unclear, noisy, limited as a description of what we want to learn. For me, a bigger question, however, has always been that this is not how animals learn most of the time. If we see humans as the golden reference for intelligence and learning, and we want to discover how to learn in a similar way, then we might want to pose the learning problems in an unsupervised setting to start with. Probably, working in the supervised setting does not allow us to think in a very new way, as we can always take the labeling shortcut. What can we learn from a set of random images? Is it possible to learn anything at all? Without making any assumptions, it is not possible to learn much. Indeed, any method that currently falls under the unsupervised learning umbrella introduces some precise assumptions on the data. For example, the data forms k-clusters, or that data is the linear combination of a number of statistically independent signals, and so on. However, there is a major difference between supervised learning and the assumptions in unsupervised learning. The supervision signal in supervised learning is per sample, while in unsupervised learning, the supervision is per data set. In unsupervised learning, we specify the general properties of the data, and in a way we label all data with a single rule. Ideally, we would want to achieve this objective by defining a very simple learning principle. This is more powerful than expected. In the general unsupervised representation learning, one builds features which can be transferred to other tasks and yield a surprising performance. However, in general, these features do not have a specific interpretation. What is more surprising is that one can do a lot more than that. One can even learn the viewpoint, the segmentation, and the 3D of objects, and the detection of object landmarks without any per sample labeling. This has been claimed often in the past, but with some hidden manual labeling, which may have created disbelief that a fully unsupervised approach could work. However, I will now show some recent examples from my group that show that this is indeed possible. There are also other recent works in literature that show similar achievements. A first example is a recent work with my student Adam Bielski, where we learned to segment objects in an unsupervised way. The key idea is to build a generative model that learns to generate foreground, background, and mask layers, which then are composed to yield the final image. The key property that we exploit is that a foreground object must be shiftable. That is, even if we slightly shift the foreground and its mask relative to the background, the composed image should still be realistic. If the segmentation is incorrect, then a small shift would immediately reveal an unrealistically deformed image. This is the general property of the data that we introduce as an assumption. The seed of that idea was actually created in 2015 with Attila Szabo and Andrea Vidaldi, where we aim to perform unsupervised viewpoint estimation. The method required to propose a family of 3D objects, we use planes for simplicity, simulated a small rotation in different directions, and then assessed the realism of the rotated image by comparing it against a large dataset. Correct 3D shape hypothesis would lead to realistic deformations. In these two figures, the off-diagonal images show some realistic viewpoint changes of the diagonal images. Here is an example of images that have been linked to each other based on the estimated relative viewpoint by using the procedure just described. As you can see, the sequence shows real images of airplanes that have been automatically sorted so that the viewpoint undergoes a 180 degrees change. The most recent iteration of this approach combines the viewpoint, 3D, and foreground and background textures into one interpretable representation. This representation of the scene is the output of a generative model. Then we perturb the model by changing the viewpoint and feed the representation to a renderer to create a new synthetic view of the scene. A discriminator then decides if the new image is realistic or not, and when trained adversarially with the generator, it forces the representation to be realistic. For example, a flat 3D would be easily revealed by a side view. This principle of perturbing a model to validate its robustness is the same principle we used in the segmentation approach that I illustrated before. Notice that this approach is fully unsupervised, as any assumption that we make applies equally to all the data at once. You can see in these examples that the rendered faces, shown on the leftmost column, 3D, shown in the second column, and textures, unwarped on the Cartesian plane in the third column, are all quite realistic and of high quality. The fourth column shows the background texture, also unwarped on the Cartesian plane. And finally, the last 5 columns show different viewpoints of the foreground object alone. Notice that the generated 3D representation is not a depth map, but instead a mesh of triangles. I hope I have now given you enough examples to show how far unsupervised learning could take us. Then, let's now get back to unsupervised feature learning. Our objective is to build features that allow us to write the probability of the label y given the data x as the probability of the labels conditioned on the pre-training features. Ideally, as I mentioned before, features should allow one to use a simple model, for example, a linear classifier, to map the features to different tasks. However, let's try to define this more precisely. What features do we want to learn through self-supervised learning? One approach is to encode each image to a unique feature while at the same time reducing the data dimensionality. This is the representation obtained with autoencoders. It is also possible to obtain representations with some local invariance, for example through some data transformations by using denoising autoencoders. Features implicitly define a metric between images. Another option to design them is to impose constraints that change the metric in desired ways. For example, we might want features that share a similar high-level attribute to be closer than those who don't share it. With high-level attribute, I mean something analogous to the global structure mentioned by van der Oort et al. In the Contrastive Predictive Coding paper. In any case, in the next slide, I will try to define more precisely what a high-level attribute is. A reasonable definition of attributes is that they are the statistics of random variables that are related in a hierarchical manner. That is, variables that are linked to other variables through compositionality. And of course, we're familiar with this structure as this is used in most neural networks. So then, by defining a suitable pretext task, self-supervised learning can affect what attributes our features cluster around or do not. An example of a simple local attribute is the color histogram. This kind of attribute may be useful for basic tasks, but it is certainly not powerful enough to perform object classification or detection. We refer to such attributes as local, as they characterize statistics of only small sets of pixels. Indeed, color histograms are the most extreme case where the set consists of a single pixel. We argue that global attributes, that is, attributes that characterize the statistics of many pixels, allow instead the solution of more advanced and sophisticated transfer tasks. Later, I will show some methods that explicitly focus on building features can discriminate global attributes. Also, in the next slide, we will see another example to illustrate the importance of the globality of attributes. An important difference that I would like to make is between local and global attributes. Here is an illustration of this distinction. Suppose we take a data set of images and then design a transformation that preserves the local patterns but randomizes the global patterns. This can be achieved, for example, by splitting the images in a 4x4 grid, by scrambling the tiles, and then by inpainting 2 pixels of the borders between the tiles. We then want to see if features can be used to tell the difference between one set of images and the other. If that is the case, then these features are also capturing patterns that are larger than a single tile. Turns out that a linear classifier trained on COM5 AlexNet features trained via supervised learning achieves 78% accuracy. Our recent self-supervised learning method, not trained with this data, builds features that achieve 85% accuracy. It seems that supervised learning focuses on features that allow discriminating mid-range texture rather than more global structure. So this raises the question, what features do we expect supervised learning to build? The simple answer is that it learns whatever is sufficient to solve the task. If texture is sufficient, then there may be no incentive to learn beyond that. However, we know that features that can discriminate more global patterns generalize better. The pretext task defines implicitly or explicitly what attributes or features can discriminate or be invariant to. To understand the effects of different pretext tasks on these two aspects, it helps to think of the induced metric in the feature space. Consider, for simplicity, that a Euclidean distance in feature space defines a distance in image space. Then we can affect this image distance by pushing features apart or towards each other. For example, we could impose that data transformed through data augmentation should be mapped nearby. We can categorize many of the existing self-supervised learning methods as discriminative and aligning ones. The first group specifies what images should be separated, but does not describe explicitly what images should be close to each other. The second group specifies the opposite, what images should be close, but is generic or uniform in what images should be separate from other images. In the end, all self-supervised learning methods, old and new, define some heuristic principle that applies to all data equally. Indeed, this is the unsupervised learning alternative to per-sample labeling. Let's now see some examples of both families in the literature. As a first example, let's consider the self-supervised learning works of inpainting and colorization. In the inpainting case, the transformation of the data is to remove a set of pixels and the task is to reconstruct the missing part. In the case of colorization, the transformation is instead to remove color and the task is to recover it. In terms of attributes, one could argue that the reconstruction of the missing part or colors requires discriminating statistics of many pixels, as the tasks cannot be solved by using local observations such as patches. In terms of the way they act in the feature space, we could consider them as aligning self-supervised learning methods because they map images which are invariant under the transformation to similar features. For example, images that yield the same grayscale intensities. As a second example, let us look at the methods based on determining the spatial configuration of parts. In these methods, the task is to train a network to encode parts as features, and then a second network to determine the correct order of the parts given the features as input. Features trained with these pretext tasks should allow the discrimination of the different parts of an object. Since local attributes are not sufficient to achieve such a discrimination, for example, colors within the same object are similar, one could argue that these features need to learn global attributes, up to the size of a tile. In terms of the feature space, I would classify these methods as discriminative self-supervised learning methods, as they only specify what features should be different from each other, but not what invariance they should have. An example where the focus on global attributes is more explicit is provided by these two works by Yuki et al. The general idea in these works is to build a model that can modify only the global attributes of images, so that we can train a network to learn to discriminate global attributes. In other words, we would like to change the statistics of large sets of pixels while leaving the statistics of local sets unchanged. One way to do that is to remove a small region of pixels and then to reconstruct it by using a very limited context, for example, a square border of only 2 pixels, and to use local discriminators, that is, working on patches, so that they can only distinguish local statistics. As shown in these images, this procedure results in distorted images with globally unrealistic objects where a face or head might be missing or limbs are detached, for example. These approaches also are discriminative self-supervised learning methods, as they only define when features of real and transformed images should be different. In principle, all features of real images should move towards each other as they are all mapped to the same class. The pretext task of RotNet can also be included in the previous discussion. However, we would like to point out some other observations. The task here is to determine the orientation of an image out of 4 possible centered rotations: 0, 90, 180, and 270 degrees. One should then ask what allows the identification of the orientation. The first requirement is that the dataset does not have the same objects under multiple orientations, otherwise the task would be ambiguous. Examples of datasets where ambiguities may occur are cell imaging and satellite imaging. The second requirement is that the task requires global statistics to be solved. For example, in the case of faces, local patterns such as the eyes or the mouth or the nose could be used to determine the orientation of the image. In this final example, we have lots of methods and the vast majority of the latest ones, which also corresponds to the top performing ones. These methods differ from most of the previous approaches because they are aligning self-supervised learning methods. They define what transformed images should be similar to in feature space, but are generic on the separation of images. The supervision signal is to choose data augmentation as the family of transformations that features should be invariant to. Although this is a common and natural choice, it encodes our knowledge that the object category is invariant to a certain class of transformations. The separation force is defined by other mechanisms such as entropy or a generic repulsion between all image instances except for the data augmented ones. In 2014, exemplar CNN was one of the first methods to heavily exploit data augmentation in this way. It considered the extreme case where each image was mapped to a single category. Later methods introduced effective contrastive losses, additional heads, and also they explore larger mini-batches and network architectures. These methods have now showed impressive performance and even surpassed supervised learning pre-training in a number of transfer tasks. The reason why the recent methods perform so well is, however, still unclear. Key factors may not be just the pretext task, but also the way networks train, the losses that are used, and the optimization methods that are used for training. We touch upon these aspects in the next few slides. One difference shown in SimClear is that the network architectures have a different impact between self-supervised learning and supervised learning training. The figure shows the top 1 performance on ImageNet for different ResNet network architectures and training epochs. For example, blue dots have been trained for 100 epochs, green crosses for 90 epochs, and red stars for 1000 epochs. The green line shows the supervised learning performance, and the red line the unsupervised learning performance. One can see how the larger architectures give more a boost to self-supervised learning than to supervised learning. Since the task does not change, it suggests that the boost is mostly the result of the architecture and the feature representation that it naturally induces. The optimization and the cost function play also an important role in how well the network trains. A few papers talk about the lottery ticket hypothesis, which argues that the random initialization of the network plays a fundamental role in the final weights to the point that a sparse subset of these random weights is as performant as the final trained weights. Thus, one could think that training procedures and loss functions that adapt very much to the initialization might be more successful in building stronger features. This could explain why Sela or Deep Cluster, which adapt the labels during training, work well. Also, the contrastive learning loss alone may have an impact in the performance. As shown in the recent work of Kozla et al., contrastive loss surpasses cross-entropy with standard data augmentations. Also, Wang and Isola showed that what matters in the contrastive loss are 2 components. One is the uniformity of features projected on a hypersphere, and the other is the alignment of features that should be invariant to data augmentations. To conclude, self-supervised learning has made fantastic progress since 5 years ago. Today, a number of methods build better features than supervised learning when evaluated on a number of transfer tasks. This is very encouraging, and I expect that the performance will go even further. However, what drives the performance is still unclear. There are several factors that determine the quality of learned features, and potentially their interplay has an impact too. Also, I expect that soon, supervised learning features will no longer be the golden standard, and that all that will be learned to make unsupervised learning work better will feed back into better supervised learning training. And we can see already this with the example of supervised contrastive learning. Finally, probably a good direction to explore is a combination of both discriminative and aligning principles by using the latest methods. The work of Fang et al. Indeed does achieve an interesting performance and probably could do even better if it adopted the latest techniques from contrastive learning.
Yes, perfect. Yeah, cool. Again, thank you so much for the talk. It's great to have you here. Attendees are encouraged to ask questions via the interface. In the meantime, I have one question which sort of goes to my heart. So you've said we talked about learning global structure from images in self-supervised learning. But what we are seeing is that the more sophisticated or the more tailored we make the augmentations, the better the performance we get, which in the augmentations are kind of very low level, right? They're not changing any semantics technically. So question is, yeah, are we really there yet that we are actually learning about global and even data set structure in that sense?
Well, first of all, thanks for inviting me to this wonderful workshop. So regarding your question, I think, first of all, it's unclear whether one could say that data augmentation classifies as a low level or as a local attribute kind of input or conditioning, if you want. So there one should study it a bit better to see if that's so trivial. So you were saying that if we are there with global structured learning. Well, I think that the whole point I was trying to get across was that we're really trying to figure out what factors determine performance, because that's what we want to act upon. But it seems to me that we don't know. And it's not to discourage anybody, but that we should be a bit careful, because we tried really to focus a lot on the pretext tasks and thinking very much about standardizing all the rest of the procedures. But it turns out that the other procedures, so the way we train, the losses we use, and blah, 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 they are not yet settled. You can still gain a lot from that. And that confuses a lot, I think, the whole analysis. And so we cannot really say that we are there in any sense, because I think it's difficult to, first of all, it's difficult to assess precisely what we are learning when we are not sure exactly if we are learning given a certain target, right? So the training procedure does something, but we don't know to what extent, right? If we had convex optimization, we would know. But here we are not super sure. So that is a little bit what I think makes it difficult to assess, but also to me very interesting, because it's not a trivial problem to address. I don't know if that answers your question or makes it worse.
I mean, in a way, both. I think it is kind of a riddle still. So that's, I mean, that's also what excites me. So yeah.
I mean, I do think that in the end, we should state precisely what we want or what we expect these features to capture. And for me, so far, it still makes sense that they should discriminate between statistics of as many variables as possible, as many pixels as possible. And so the fewer and then the simpler the task they can solve, and the more advanced. But then again, there are the other factors to take into account for what one can then use these features for.
Yes. So there's a question from the audience that goes along almost the same lines. Rupesh Nawaya asks, in the words of Trevor Darrow, we are doing augmentation engineering in contrastive learning, which is very much tied to the downstream task. How do you think can we move towards methods that are generalizing to unknown downstream tasks?
So this assumes that it's possible to generalize to an arbitrary downstream task, right? But clearly this is not possible, right? I can easily build a downstream task that will for sure put off, will result in very poor performance. For example, I can come up with an arbitrary arrangement of the categories. I want to put dogs and bicycles together because some reason, right? Why not? Then for sure it's gonna have a problem with that. Or maybe not as much, but I'm sure one can try so an arbitrary task, downstream task probably is impossible, but maybe one can aim for a family of meaningful downstream tasks. And maybe the criticism is more of, well, in the end, we ourselves are some form of gradient descent where we're basically fitting the downstream task by changing constantly the data augmentation. Sure, that's definitely a perspective. But from my point of view, what really matters is finding out these general properties and general learning rules for the whole data that we are working with, that we think is meaningful to work with. And if the downstream tasks help us guide us to find those, fine. I don't see a big deal with that. So I don't know if it's not a competition to me. It's about finding out how we learn from data.
Cool. I have found one question here from Yuhuang Hu, asking, how should we reduce the problem of using large batch size and longer training iterations? Are these problems tied to the complexity of the pretext task? And similarly, we had a question relating to the number of GPUs being used in recent self-supervised learning papers. Yeah, what do you think about these longer and longer trainings, basically?
Yeah, so people found that all of that brings an advantage to the performance, and that's mostly because we need to compete and have better numbers so that we can publish, right? So that's one perspective of, is this making the competition fair, right? And of course, one can try to make the competition fair so that we can evaluate things in a more even play field. But I don't know if this is easy to assess, and maybe I guess this is just about how we decide when we accept a paper or not. At the moment, we have a simple rule: if the performance is better, there's enough difference, then it's great. But then maybe we want to explore different computing efforts and so on. And because indeed one finds that the longer you train, the better it is. And then there are some training procedures that do bring an advantage. The question is then the comparison. And that's a big story also on how to evaluate different features learned in self-supervised learning. We have tried to make this a kind of a simpler task. We had this paper where we basically said, you take your pre-trained network, whatever you want, however you have trained it, and then you make it produce features from some layer, and now we cluster it, and now this is a pseudo-labeling. And now we train the same network for all these pre-trained networks, right? So now, basically, we convert every pre-trained network into a labeling of the data. And then the training procedure can be really the same for all. This doesn't seem to have taken any, basically, nobody is using this idea. And maybe there's something really unappealing to it. So I'm happy to hear, actually, any opinion on that. But this is one way to maybe make the field more uniform, so that it doesn't even matter what one is free to use the training one wants, because then the transfer is done in a precise way.
Yeah, I think so. The fairness is definitely one thing. One question which I think is related to this one is also, so some pretext tasks are just more complicated in one way or another, and they might need 1,000 epochs, versus some pretext tasks might be saturated after, say, 200 epochs of ImageNet. So do you think that, yeah, exploring both directions is good, or do we really just care about infinite training length, in quotation marks, getting the best downstream or best general features out of our tasks?
Well, I mean, what I was trying to say is that if you convert a pre-trained network into pseudo labels, then there's no difference. Then the field is the same. It's just every pre-trained feature, pre-trained network will give a different pseudo labeling, and that's the knowledge they bring to the table. Then it's quite straightforward on how you compare them, because you can use really the same secret. So then what you mentioned, that is the difference in the complexity of the pretext task and the networks, and that is all done in the pre-training. But then once it's done, so one then can be free of doing that. But once it's done, and then now you tell me how you label things. And maybe you could say, well, k-means clustering is not the right thing, because who tells you that an L2 norm is the right distance in feature space? Fine, you know, we can choose whatever metric, but then it's the same for all. And maybe we can argue that it's a good thing to keep that distance simple in the feature space. So I don't know if that is what you were looking for.
So what I meant is, for example, if there were a method that just trains for one epoch and gives you 50% resonant performance, which isn't state of the art, but it's for one epoch, it would be crazy good, I guess. But it doesn't improve after the first epoch at all for some reason. Since we only care about the final performance, this would have a hard time, I guess, getting anywhere. Because
but
as
you're talking about the pre-training, right?
Yes, the pre-training itself being quick. The downstream task could be normalized via like clustering or via some normalized evaluation metrics.
So your question is what I think about the fact that different methods require different training times and
yeah.
Well, this is the part we don't fully understand, right? Of how neural networks train. But in terms of the comparisons and the competition, for me, one can just pick their best training, their best pre-training. I don't know if again you're.
Yeah, no, I think it makes sense that you would just try to get the best out of your method, and that's because we only care about or mostly care about the downstream tasks.
Yeah.
So we have one more question that we can answer in this time slot. Nupur Kumari asks, there are various ways proposed to solve domain robustness, like adversarial training or different kinds of self-supervision. How can we probe the network for the difference in what it learns from the different objectives apart from measuring performance on downstream tasks?
So basically, this is about evaluating the features learned by through self-supervised learning, right? Yeah. So that's a huge question, and indeed, this is an open problem. So we have these ways through the downstream tasks because that's useful. So it's great to definitely do that. We all know that. We are exploring some other directions actually just recently to see how these features really can allow the characterization of the distribution of data sets. So if we are successful, that could be another way to assess them. And then, of course, there are several other works that have looked at what objects, what textures, and so on they pick up. I would say, again, my perspective is, as I mentioned in the presentation, that I think of unsupervised learning as being the last goal. And the fact that one can learn really even interpretable representations, shows that you can really, maybe in the end, the labeling is just giving name to things, but it's not necessary. You can call something A, or you can call something a car. It's kind of, it should be, to the point, it should be relevant, that. And of course, then we all know that we need at some point to use them for specific tasks, and then fair enough that one labels things. But in terms of measuring the performance, maybe we could move the field more in not a supervised setting, but maybe in a different setting, where we just assess the properties of self-supervised features. For example, I showed in one slide that we tried to assess supervised learning features by modifying the data so that we modify only or approximately only the global structure of the images, and try to preserve as much as possible the local ones. Then you can try different sizes, and you can try to see how these features really are able to discriminate these statistics, right? And like that, you can do it for many other things, and also with videos, you can do that over time. But that's all unsupervised, right? So that's all to artificial tasks, and I would say that has some value in that characterizing the properties in an unsupervised setting, to me, also says something. Of course, I know there's a strong push to stay within the supervised tasks, because that's a direct usage that justifies the.
I think this is a very, very interesting direction as well. Also, in personal experience, the big problem is when developing self-supervised methods is that you always have this two-step process. You train your self-supervised task, and then you have to evaluate your features, which takes another day or something like that. If we had something to, on the fly, understand how good these features are, a lot of progress could be made much quicker, I think.
Well, like
yes,
clustering, self-supervised learning via clustering, you can always evaluate the clusters, how well do they correspond.
Yeah, and that is an unsupervised way to assess.
Yeah.
Of course, if you could also look at the labels.
Yes. I think we have to start the next talk. Paolo, it was a pleasure. I hope you stay around, and yeah, talk to you later. Then.
Thank you very much.
Thank you.